into, with page 43, some physical applications. All right, so we're talking about mass density. I'll just read the definition. Mass density of an object is defined as mass per unit volume. All right, so it kind of begs the question, if we can figure out the unit volume, all right, we learned techniques for finding volume, then we can find some other things associated with the physical applications like mass density. This parameter can be expressed using several different units, including kilograms per meter cubed and pounds per square foot. All right, I got to fix that notation. Mass density is represented by the lowercase Greek letter rho, although the Latin letter d has historically been used as well. We're going to use rho. All right. So we have this formula where rho is equal to mass divided by volume. But if I wanted to solve for mass, so we have rho is equal to mass divided by volume. If I solve for mass, put the rho over 1, I would get mass equal to rho times volume. Okay, so that's going to be the major component here, coming up with this idea of mass, but based off of its relationship with mass density and volume. All right. So mass density is representation of the amount of mass or number of particles of a substance, material, or object in relation to the space it occupies. All right, which would physically make sense. All right, so however, this measurement is not necessarily constant. Mass density depends on several factors, including temperature and pressure. All right, so here's the scenario that we'll be working with, given a thin rod oriented along the x-axis over the interval of a to b. Let rho denote a linear density function, giving the density of the rod at a point x in the interval. The mass of the rod is given by m is equal to the integral over the interval of a to b of rho of x dx. All right, so very simple. If you have this relation to find the mass over the interval of pi over 2 to pi, rho is given to be sine x. It's oriented along the x-axis. So it's really just asking us to evaluate this integral. So from pi over 2 to pi sine x dx. Now we will need to discuss where this rule came from, this formula, and why we're able to use it and what its value is, but for now it's just a skill. All right. Consider a thin rod oriented on the x-axis over the interval of 1 to 3. If the density of the rod is given by this polynomial function, what's the mass of the rod? So, very simple. Over the interval of 1 to 3, we have 2x squared plus 3 dx. And again, right to the calculator, math 9. Use Desmos if you like. 2x squared plus 3 dx. And we get something that's frackable. All right, so math enter. And we're looking at 70 over 3. Now, they didn't give us any units here. It's a measure of mass, so it could be kilograms, could be grams. All right, so we'll just say units for now, but with the idea that it could be modified later on, right, depending on what the scenario dictates. Some of the theory behind it, really what's happening here is, because again we have rho equals mass density divided by volume, which means mass density is equal to rho times volume. By the way, you may have noticed I made some edits to the page mid recording, so that's why some things are subtly different, like a capital changed into a lowercase, things like that. All right, so this is the correct version. So if we were to take, and I'll just do a quick diagram, if we were to take some function that's positioned along the x-axis over some arbitrary interval that we'll call a to b, what we would need to do in order to come up with the mass density of this figure would be to multiply the density of the object by the object's volume. All right, so since we're being given for these problems a thin rod, what we're going to do is we're going to assume, in the next page we'll change our assumption, but we're going to assume a volume equal to 1. All right, so we're looking for the product of the volume and the density. Well, if we're assuming one of them is equal to 1, then that's just going to give us the other. Well, and in fact, it's really more like we're assuming the area over an interval is equal to 1, because as you might remember, volume is area times d something. And let me actually write the word area so I don't confuse everyone. So it's actually really not the case that we're assuming volume's equal to 1. It's more like we're assuming the area over that bounded region is equal to 1. So the area is equal to 1, in which case volume would be equal to 1 times d something. All right. And so if we're going with rho of x, then it would make sense to go with a dx. All right, and this would be happening over the interval of a to b. All right, so then the question would be, well, how on earth could you assume that the area is equal to 1? Well, we got to assume it's equal to something. It's a thin rod. All right, so a thin rod would have, we know the thickness is going to be accounted for in terms of the, or accounted for in giving us the volume, all right, because that's just really giving that thickness as it revolves around the axis. So, I mean, I'll draw my usual terrible sketch. So I'll do this in blue maybe. So this is that half circle, the semicircle, right? So, and if we piece together the other half, we would have the full circle. So something's getting revolved around here. We know that the thickness dx is going to help us get the volume. The volume here would be pi r squared h. So what I'm saying is that the h, again, being the dx, the pi r squared being the area, that area is going to amount to a 1. All right, for our thin rod instance. All right, so I mean, if you want to, what you can do is take the pi r squared, set it equal to 1, you get r squared is equal to 1 over pi. So the real assumption here is that we're claiming that some bounded region is revolved around the axis, and that bounded region has a constant radius of the square root of 1 over pi. All right, so very small, you know, about half a unit, a little bit more than half a unit. All right, so that fits the definition of a thin rod. All right, rod as in being cylindrical, you know, kind of like a straw, I guess, but having a diameter of about a little bit more than 1 unit. All right, so that would suffice in being defined as thin. So what we're going to do on the next page is evolve this into a case where we're looking at something that's not just a thin rod being revolved.